Thank you. My name's Brent Wesley. I'm one of the local networking people here in Gladstone. I'm going to try and delve you into the world of IPv6 and give you a little bit of a basic understanding of how it works and a bit on configuring some routers, some pfSense and OPNsense equipment to start people off from using it, engaging with it, because we need to transition to it. Firstly, I'd like to acknowledge actually the help of Terry Sweetser from APNIC. He's been very helpful to me this week to give me some guidance and some additional information, which I've incorporated into my talk here today, so thank you, Terry. He is also, has been discussed this morning, he's got a training session on Friday here at the Gladstone Incident Centre on Introduction to IPv6. If you get out of something today and you want to further your knowledge again, Terry is probably one of the most knowledgeable people on IPv6 that we could have access to, and he is a great resource. Take advantage of him if you can. So the aim of the talk today, as I said, we want to basically give you some understanding and some mechanics around IPv6 and give you a working knowledge so when you go to configure a router, you understand why we're configuring things the way we do. Unless we understand it, we can't. This is by no means going to be a comprehensive tutorial, but hopefully you do understand enough to be able to engage with it afterwards. In the second part, I'll take you through some configuration steps for pfSense Community Edition and OPNsense. If you're not familiar with either of these products, they're based on Monowall originally, which was a router platform written under FreeBSD. OPNsense was forked from pfSense in 2015 when pfSense was purchased by Netgate. Other than the obvious advantage of a ridiculously large amount of IPs, there are a lot of other advantages to IPv6. The removal of the requirement for NAT is a big one. While NAT still does exist in some scenarios for IPv6 where you're doing a dual stack, it's typically no longer used. Improved security with end-to-end IPv6 communications and things like inbuilt support for protocols like IPsec. Simplified routing leading to lower router overheads and increased speed. A streamlined header structure with native support for an extended packet header. Native QoS support, and protocols like Slack or stateless address auto configuration, which means less need to configure IPs for end systems, including the use of DHCP, and better handling for packet fragmentation with automatic path MTU discovery. IPv6 addresses are 128 bits in length, as opposed to 32-bit for IPv4. IPv6 addresses are represented in hexadecimal, unlike the decimal system of IPv4. Each address is made up of 4 bits, or a nibble, to represent a hexadecimal digit, and you have 4 nibbles, or 16 bits, that make up a hextet. In an address, this is represented as 8 hextets, or 4 nibbles, or 16 bits, and each separated by a colon. So we have these big long addresses, but they can be shortened. First rows within a hextet can be removed. And secondly, you can replace contiguous hexet segments of zeros with a double colon. A double colon can only be used once to avoid address ambiguity. So you can see that big long address has 2001 OD B8 0000 0000 036E 1250. That shortens down quite a long way to 2001 DB8 : 36E 1250 2B00. So a big difference. Network addresses. IPv6 network addresses are made up of 2 sections. There's the host prefix and the host bits. The network prefix and the host bits. The network prefix is made up of two parts. You have the customer site prefix, which defines a group of subnets, and you have a section there where ISPs or RAAs would assign either, say, a /48 or a /56. And then you have a subnet ID. This defines the subnets or links within a site. The second block of 64 bits is the interface identifier host portion of the IPv6 address. Subnetting in IPv6 is similar to IPv4, but it's structured so that LANs have 64 bits of network prefix as opposed to the variable length of network prefix in IPv4. In IPv6, a /48 is the smallest size subnet that can be routable in the global scope, and I'll go into that in a little bit. Here you can see some common subnets that you'll hear referenced quite a lot through this talk. So we've got a /128, which is obviously one address, a /64, which is 18 quintillion 464 quadrillion 764 trillion 73 billion 709,551,616 addresses. That's in a single /64. That was a mouthful. And then we have a /56, which is 256 subnets and so on. Here's a larger breakdown, and this is certainly not a complete list, but it gives you some indication of the scale of IPv6 subnets. So a /48 obviously has a single one, has 256 /56s and 64,000 or 65,000 /64s. We get a lot of IP addresses. So I want to discuss scopes a little bit. In IPv6, say we've got a typical local network. In fact, we can have multiple local networks or subnets within each with its own router. These local networks sit behind a router that's connected to the internet via IPv6. Let's wait for the drawing to catch up. When we have an address that is routable by the internet, it is part of what we call the global scope. An address prefix that is given to you by your ISP to be used internally as part of your network is referred to what's called a unique local scope. And hosts on a local network within the same collision zone or switch are part of what's called the linked local scope. Now, these terms are quite important to understand because they've referenced a lot later. Next slide. IPv6 has several reserved special address ranges, and these are some of the most common ones that you'll see referenced a lot. So /128, which is local loopback, /128 represents an unspecified address. 2000:/3, that is the global unicast address range used for global routing. FC00:/7 are used for unique local prefix. And FE80:/10, this represents the reserved linked local unicast prefix. So for hosts on the same collision domain or the same switch. One thing that I haven't touched on yet is that IPv6 is heavily dependent on multicast. It is the backbone of the network. Unlike broadcast, in IPv4, there is actually no broadcast used in IPv6. To aid in multicast, there are a number of special addresses just for multicast. We've got FF02:1. This is basically send to all nodes within the network segment. FF02:2, which is send to all routers on the network segment. FB, which is multicast to all MDNS agents on the network. :1:2, multicast all DHCP-v6 servers and relays. And O2:101 is multicast all NTP servers on a segment. ICMP is probably the most crucial protocol that's used within IPv6 for control. It's not just a handy tool for checking if another host is reachable. It forms part of the process for obtaining a network address, as well as other things like forming part of the functions like automatic path MTU discovery. ICMPv6 extends the ICMPv4 protocol with a few new essential types. I don't know if anyone's ever looked into IPv6 on Wireshark, ICMP on Wireshark. You would have seen existing types like type 1 and type 0 already in there. 133 is router solicitation, or RS. 134 is router advertisement, or RA. You've got neighbour solicitation at 135, neighbour advertisement on 136, and 137 redirects to a new best next hop. Router advertisement service, or RA for short, is used on each network segment to tell a host that how to configure their network address. An RA is fundamentally configured in one of 5 modes based on what your requirements are. You've got router only, where the RA only advertises its own presence as a router on a segment. You've got unmanaged, where the RA instructs all clients to use Slack or stateless address auto configuration to configure their network address and all the information, other information like DNS. You've got managed, where it advertised hosts to use DHCPv6 for all address and additional information. You've got assisted, which will allow you to use both Slack and DHCPv6 independently, and stateless, where Slack will be used for address assignment with the additional information like DNS, NTP, and so forth provided by DHCP. ICMP again is used for this, and it's the type 134 and 135 used to communicate to that FF02::2 to communicate with the RA. NDP or ND, as it's known, is the Neighbour Discovery Protocol. NDP is a direct replacement for ARP that's used in IPv4 to detect the link layer address of a neighbour. Like RA, it's an extension of the ICMPv6 protocol and has additional functions like providing services like DAD, which is duplicate address detection, and neighbour unreachability detection. So it uses the 135 and 136. So if we look at this diagram here, we can see, okay, we've got a machine that wants to talk to the index, so it wants to do a ping. It sends out an NS type 35 message that includes the source address of the originating computer and the destination of what it's trying to talk to. When a device joins an IPv6 network, it joins what's called a solicited node multicast group. And it uses that to see if any other devices on that network are trying to communicate with it. So when it sends out, it's sending to that multicast group, and there is actually a special subset of the address prefix that is used for talking to that multicast group. So the source address it's trying to contact, and the multicast group for that interface. The destination device that's on that multicast group listens to that NA message and responds with its to that NS message and responds with its NA message containing the source of the address of it, the return destination back to the original node, and the address of its link layer or L2 address, so its MAC address. Like ARP, IPv6 devices keep a table of discovered IPv6 neighbours, much the same as ARP. Unlike in IPv4, hosts on an IPv6 network normally have more than one address. This is to allow things like different scopes to establish end-to-end IPv6 communications, which enhances security, removes the requirement for protocols like NAT. Typically, if you were to look at an interface of a machine that is on an internet-connected IPv6 network, you'll see a number of addresses, including a linked local address, which is used for local communications on that network, and a unique local address that's either configured by Slack or DHCP-v6, depending on how you configured your RA. If you're on a Windows or a Mac OS machine with IPv6 and you've configured your unique local address with Slack, both of these operating systems have implemented something in addition that is not currently built into Unix at the moment, or Linux at least, and that's RFC 4941, which is IPv6 privacy extension for Slack. Essentially what it does is creates a temporary insecure address on the link local for that specific connection. On some machines, depending on how many connections you've got open, you may see 50 or more temporary addresses if you look at the interface. Don't be alarmed by that. It's part of the system, and it destroys those addresses after that connection's been closed. Network addressing. So in IPv6, we've got three methods essentially of assigning IP addresses. The first, like IPv4, is static addressing. This is still a valid method within IPv6, but it's less commonly used because we've got better ways of doing it now. Slack, stateless address auto configuration. This is the method that is the default method for creating linked local addresses on your network, and will always be used to initiate a connection and be able to talk to an RA. There are new extensions. There is also the extended DHCP v6 service. It carries some additional advantages over Slack, plus some penalties, but requires that the server be running on the network and the RA to be configured to point to it. If running in stateless mode, it will not be stateless mode on the RA. It will not be responsible for actually issuing the network the additional information like DNS servers and DHCP options like bootp and SIP control. So if you need those on your network, you really need to look at DHCP. We'll cover Slack. So say I have a device on the network that wants to talk to the internet. I first need to create a linked local address. It's not talk to anything, so it needs to create a unique address on that network. So there is a number of methods and there's preferences along the way for doing this, but at a basic level, we can use our MAC address to form part of the address. You can see there we've got our MAC address and a linked local address on the network. And we've got a router that's already got that built in as well, so it's got its MAC and its local address. We send out a multicast ICMP type 133 router solicitation packet to FF02::2. That router has already got a connection to the internet, so it's got a global address. It's got its unique local prefix, which has been assigned to you by your ISP, and the length of that prefix. Once it's received that router solicitation, it returns back to the original device a router advertisement that contains the network prefix and any configured things like DNS and routing information. You can, with Slack now, advertise additional routes that you couldn't do initially, but that can now be done. DHCP v6, it's very similar in the way that it works with than Slack, and it uses the same mechanism to establish the initial connection. So it will send out a router solicitation message, so that's wrong on the slide, to the router, and it will return back with its router advertisement saying, hey, I need you to configure via DHCP. It then sends back to either the same router or to the service, to another service, a DHCP solicitation, gets back its advertisement, chooses what it wants to see and sends back the request for that address, and the service will say, yes, okay, I'm happy with that, you can use that address, go ahead. It then configures its unique local address based on that. DNS. One of the biggest complaints, and I believe this myself, and to up until recently when I started dealing with with IPv6, is that the addresses are too hard and too long, and I can't remember them. We're all gotten very good at remembering IPv4 addresses, but guess what? We don't need to. Unless your memory skills are insanely good, you won't. IPv6 has been fully implemented in all major DNS servers like Unbound and Bind. For practicality, we need to rely on DNS, including in our own local networks. Luckily, we have modern DNS alternatives environments with services like MDNS. Both Bonjour and Avahi fully support IPv6, and even some newer networking protocols like Thread rely on MDNS being functional on a network using IPv6. It is solely built around it. There is an addition to DNS in DNS v6 of an AAAA record, or what they call a quad A record. And it's a direct replacement for the A record we're all used to in IPv4 DNS. The simple difference is that it allows for the 128-bit address. The other difference with DNS is that notation for the reverse DNS zone has also changed slightly. So instead of the in-adver.arpa, we now use ip6.arpa. Now, I'm going to preface this section on the talk on configuring pfSense and OPNsense by saying what I'm showing here in configuration is what I've encountered with a number of ISPs in Australia, particularly on the NBN network. Of course, your provider may dictate a method that's different to what I'm showing here, but how you join doesn't really matter. Most of what I'm saying will apply to what you do. So what do we need to know about IPv6 for our internet access? First and foremost, we need to know the configuration setup from our provider. We need to know what size prefix they allow, because every provider is different. How you're going to configure our unique local address allocation, our router advertisement mode, what subnet prefix you're going to use assigning to an interface, and how you're going to handle DNS allocation. As a little side note around ISPs in Australia, each of them are at a little bit of a different stage in terms of the maturity of their dual stack. Some are very good, some are not. There is no hard and fast rule as to what size prefix they will issue. Some are actually allocating like a /48, which is actually probably the majority, but some are actually only giving out a /60 prefix. Now, it's still a stupid amount of IPs, but it may come down to how many subnets you have on your network that you may exceed the 16 subnets that you get with a /56. So you do need to take that into account on larger networks. The other thing that I've noticed, particularly with one provider in Australia, is what they call the IANA timeout, which is formed by part of what they call the DHCP prefix delegation. And that varies wildly between different providers. Some are set to 5 minutes and some are set to effectively indefinitely. What this means, so Superloop is the one currently set to 5 minutes. And what that means is every 5 minutes, it's rechecking whether you are still allowed to use that prefix. Now, because they are doing it every 5 minutes and every client is trying to do that every 5 minutes, their current setup is getting overwhelmed and they get timeouts. And during that timeout period, you will lose your IPv6 prefix, which is not good. You're streaming and suddenly your stream stops and then resumes and stops, particularly with YouTube. I've spoken to them about this. They are aware of it. Currently, their engineers pretty much don't care. Where there are other providers that do set it either up to a day or longer, and they don't get timeouts. So your mileage may vary as depending what provider you are currently with. As far as I can see and research, and there's no real definitive list that I can find, there's no ISP within Australia that currently offers static IPv6 unique local address assignments to your network, certainly on home and small business plans. So take that into account. Once again, DNS is going to be key. pfSense and OPNsense. I was hoping to have a live demonstration here today, but unfortunately our network wasn't going to give me what I needed to be able to effectively show it on screen. So I have got slides here which I'm going to fall back to. So please bear with me. It's a little bit vague on some information, but you'll get the idea. Just quickly, who here has worked with pfSense or OPNsense? Just a quick show of hands. Okay, that's good. This is very, they are quite a generic product. They're certainly not your consumer grade firewall that you'll get from Aussie Broadband or something like that, but certainly a lot more configurable. They are based on BSD, they have a lot of flexibility, and they are quite easy to configure. So what we'll look at is enabling IPv6 on the WAN interface, the address mode, enabling IPv6 on your LAN interfaces, and you may have multiple. So the address mode, whether you're using what's called a track interface, and what that prefix links that you're allocating to each of your subnets are. Setting up an array, so we're looking at the router mode, DNS configuration, and enable and configure DHCPv6, so on. So firstly, we need to configure a WAN interface. So we go into the WAN interfaces by going to interfaces and then selecting WAN. Hopefully you've got this all pre-set up in your device. And we set, there's two sections there, one for IPv4 type and one for IPv6. Now, most providers in Australia under NBN are using DHCP6. Some, depending on whether you're on fibre to the node or fibre to the curb or fibre to the premises particularly, they may vary in that they require PPPoE for routing, for integration purposes, but that's part of your pre-work that you've done. And it won't generally vary from what you're already doing with IPv4. Once we've got that, we also need to specify further down on the page, there's a section there for DHCP-v6 prefix delegation size. So that's where you're saying, okay, this is the size of the prefix that I want. You can leave it blank, but a lot of providers will fail the connection unless you've got that. There is also another section there called prefix hinting. Some providers in Australia do want prefix hint. If you end up with a global address, but you're not getting your unique local prefix, try using the prefix hint. Once we've done that and we've got a working connector, you should actually have a global address. It's simple as that. So on the main dashboard page, you'll see under the interfaces that we've now got a configured global address. That's only one half of the equation. The next step is to make our unique local prefix that we've been allocated available on our network. Obviously, if you've got more than one interface, you'll need to do this for each one. But under each interface, so in this case, we've only got the one, we'll go into it and we'll configure the type. Now, you can use static and route addresses directly, but the most efficient way, particularly if you're using DHCP6 for your addressing, is to use what's called track interface. Track interface lets us link our LAN interface with a unique local network that's been assigned to another interface. So in this case, we want to be able to link it to our WAN interface, which has already been given that prefix. We then give it a prefix ID, which comes into the subnet part of our initial network prefix, and you assign a subnet to each interface. What that will do is then give each interface a /64, typically, and you can override it if you really want to get into it, but you can allocate a /64 to each of your networks. So if you've got an IoT network, a guest network, whatever, use a different prefix ID there. Remember, it's hexadecimal, fall within the scope. just use 0 if you've only got one. Once we've got our interface configured, we need to set up our array. Under services, we select router advertisement, which will only show once you've got a working IPv6 interface. You won't have seen it before if you haven't. We need to set the mode for our array based on how you want to configure your clients. So choose whether you're going to use Slack or whether you're going to use DHCPv6. In recent times, Slack has become the preferred method on assigning addresses, but it's purely up to you as to what you want to use. Whatever you're comfortable with. And if you do have that DHCP option requirement for VoIP or for BootP or something along those lines, also you're going to need to use that. If we're configuring Slack, on that page at the bottom, you'll see a section for DNS advertisement. You'll also further up on the page, which I didn't grab, sorry, it is on that one there, you can see array subnets where you can advertise additional routed subnets to that network. So we can specify our DNS servers right there. Obviously, there's actually nothing stopping you using an IPv4 address there, but you'd be crazy if you did. So specify your DNS server or servers. You can actually, there's an option there for mirroring DHCPv6 DNS configuration. So if you have both on your network and you want to use one as your master source, you can tick that option, and when it allocates out via Slack, it will give out the same information. Quite a handy little feature. DHCPv6, if you require it on your network, head into services and then DHCPv6 server, and you'll see one for each of your networks there. Recently, I think it was about 6 months or so ago, they transitioned pfSense from IC DHCP, which was the old one under FreeBSD, to Kia DHCP. The configuration is no different depending on the version of your device or VM, will depend on what you will. If you're reusing the old one, you might get a nag message. I'm using the newer one. There's no downside to it. It's configured the same. It's just under a newer stack. The main option there, as with any other DHCP server, you need to configure your address range. You'll actually see there on the screen the prefix that's been assigned to that interface based on the track, and that it's a /64. So you've just got to give it basically address range and be as little as generous as you like. There are actually some common words that people use within network addressing because we can do it, and that can make remembering things a little bit easier. You can certainly use : :1 or to : :ff, or you can use words like beef and cafe and food because they fall in within the hexadecimal addresses. So if you want to make it a little bit more memorable, as long as it's a range that works for you, go ahead and do it. As with every other DHCP server that you've probably configured 100 times, you've got all your other options there for extra settings and so forth. You've got your DNS servers, you can specify NTP servers and so on. There's your NTP. You can still use static assignment. The difference with IPv6 static assignment, it uses what's known as a DUID instead of the actual MAC address on the device. If you actually look at an interface, if you're on Windows and you go ipconfig all, you'll actually see the DUID for that device. There are other methods for looking it up. I can't remember what at the top of it is. Top of it, it's probably IPA will probably tell you the same thing under Linux. That is actually the reference that you actually put in for your static assignment, not the MAC address of the device. From there, you can basically give it whatever whatever address you want in within your range. Under that /64, give it a host name, whatever you want to do. Firewall. Now, pfSense by default out of the box, uses automatic firewall rules. If you're like me, I don't rely on automatic. I build my own firewall rules, and there's certainly what they call, there's hybrid mode, which is a mix of what they create automatically as the anti-bogan networks and so forth, and then your own ones, or strict mode where you're creating everything yourself. If you are at that level where you are creating, you will need to create a firewall rule, obviously very similar to IPv4. You just need to either do a single rule that is going to cover both IPv4 and IPv6, or create a separated rule if that's your preference. But just bear in mind that if you aren't running in automatic mode, you do need to do that. The one thing that you don't need to do, unless you're in an environment where you need to do, say, 6-to-4 NAT translation or 6-to-6 NAT translation because of certain requirements like site-to-site communications or something along those lines, you do not need to configure NAT. That's gone. Hooray. Sorry. Once we're up, that's basically, so that's what a firewall rule sits in the configuration, pretty basic. Once everything's up, you can go into status and then into interfaces and check both the WAN and LAN. They should have, certainly the WAN will have its global address, and the LAN will have a unique local IPv6 address, and you'll see the prefixing and any relevant gateways and DNS. At that point, you're up and running on pfSense, hopefully. You should be able to go to any command line, do ping 6 or whatever, and go to Google, and you should get end-to-end IP communications under IPv6. There are a number of websites like IPv6-test.com, and that will do end-to-end IPv6 checking for you. Good tool to have. There are a lot of lookup tools and stuff like that, and you will start taking advantage. And all operating systems now preference IPv6 communications over IPv4, so you won't need to do anything. OPNsense is almost identical, given that it's the same underlying platform, so I'm going to cover this very briefly. The UI for OPNsense, I don't run OPNsense myself. I basically did this for part of the talk. It's got a more modern feel, essentially. They've got people that aren't handed to corporate environments like they have with Netgate and pfSense to changing the UI, so they have a more modern UI for their environment. So where stuff is a little bit different. It's a bit slicker feel, but what I've actually found is that under the hood, it's an older core than what pfSense is. There's more development that has gone into pfSense than there is with OPNsense. Obviously, they were based both off the original product. WAN's configured under interfaces and then WAN. The configuration options are almost identical. You really shouldn't see any difference. If you're looking at a guide for pfSense and you're trying to find one for OPNsense, you can just follow the pfSense configuration. Same goes for LAN. You're configuring it under a track interface and specifying the track interface and what your subnet prefix is, subnet ID. Router advertisement, again, exactly the same as pfSense. Set your mode, and if you're setting things like DNS and NTP and routes, go ahead and do that. Any questions? No? Yeah, one at the back.
Oh, I know you.
Hey, look, thanks for the session. From your experience, where are the most common gotchas or misconceptions for, say, a small business or a home user first trying to use IPv6 with their ISP?
Good question. Look, it comes down to the nature of the device. Obviously, ISPs in Australia have been shipping out routers, their own brand, pre-configured with IP6 for a very long time. They will work straight out of the box. If you're in our world where we're configuring devices like pfSense, OPNsense, Sonic Ball, whatever vendor product you're using, they're all roughly the same. Unfortunately, the vendors are not making it so obvious that they're preferencing IPv6. They don't provide the pressure to industry to make things. Nothing comes out of the box configured for IPv6, unfortunately. And that's probably something that fundamentally needs to change within our... I think we as consumers probably need to push back on vendors and say, hey, start getting your act together and configuring devices and make the management interface IPv6 by default as a good starting point. It gets people to start engaging with IPv6. Look, it's not for everyone in terms of, particularly if you're migrating an existing network to either a dual stack, and it's certainly a very lofty goal to move to an IPv6 only network. There are certainly people that have done it. And for home networks, that can actually be achieved because there are ways to translate from IPv6 to IPv4, so you're going the other way. Stumbling blocks, ISPs seem to be a little bit of a stumbling block. Most are starting to get their act together. Their help desk environments tend to be a bit hit and miss as whether they're aware of IPv6 even, or how it affects their network and what to do when something breaks. They've been trained on how to do IPv4 for so long. They've got their scripts, they know what they're doing. By and large, it doesn't really make much difference, but sometimes you'll ring up and go, IP6 what? And they don't really know. And you go, oh, you smack your forehead. And so can I talk to someone else that knows what they're talking about? You know, there are certain vendors. Telstra seems to be quite good in terms of their help desk. They've been using, I think, IPv6 on their network probably the longest in Australia. Is that Terry? Would that be about right? I think they've been quite entrenched in it. Other carriers like Superloop and stuff like that, they've been using for a fair while, but the maturity of their dual stack environment is not great in some instances. So that's probably a bit of a stumbling block. Make sure you've got do your research on your ISP, ask some questions if you've got the ability. Certainly, if you're using carrier like commercial grade like Vocus or people like that, your mileage will certainly be a lot better with those guys. You will have direct support with people that probably know what they're talking about. That's probably the biggest stumbling block, is getting someone to understand when there is a problem, how do we fix it?
Any other questions?
I forgot my question. No, so when you so you set it up and you have an IPv6 address. Like, I feel like the part I always struggle with is I already have my IPv4 network with all my nice local DNS names for all my stuff on my local LAN. So, I mean, should you use DHCP to be able to DHCP v6 to be able to give your local devices their own DNS names? Or Slack, because Slack can't do that, right? That's where I always kind of get stuck. Do I need to run a DHCP server or not?
So it's a little bit different. So DHCP v6 and Slack do the same job essentially, in that they are just telling your network how to configure. They're not, and they're saying, here's a DNS server. Now, that may be a DNS server on your local network, like what you're probably doing, or it might be, Google or Cloudflare or someone like that. So it depends on where you want to control your DNS entries. If you're running your own servers, obviously things like that are quite important to be running locally, and by all means go ahead, and both OPNsense and pfSense. I have found Unbound, which is the preference for both platforms as a DNS server. Your mileage varies with it because it doesn't have, certainly at a graphical level within the UI, unless you want to get down and dirty with it, it can't configure local zones directly like bind can obviously has done since day one. You can, as a package, install bind. I do it, and set up my own zones on the thing, and you can set up both your forward and reverse if you want to do that. There are other alternatives. Certain ISPs, Aussie Broadband, actually give you an option in their My Aussie platform to actually specify an NS server to broadcast as part of your prefix. So straight out of the box, you're basically, okay, well, here's my upstream thing. So if you've got an external service like Cloudflare DNS or something like that you've got set up, and you want to resolve your local addresses automatically and not have to worry about an internal service, you can certainly do it that way, or even point back to a local service if you want to handle that side of things. So it's up to you. You can run both dual IPv4 DNS and IPv6 DNS at the same time. There's no issue there. They work on different ports. And it's exactly the same method of setting up your zones and stuff like that, apart from the fact that you've got the quad A record for a thing. You're still using pointer records as reverse DNS. The notation for reverse DNS entries is similar but a little bit different in that you do need to expand out the full IPv6 address when you're creating a reverse for it, and then do your reverse and put your dots in and so forth. There's a number of tool websites that paste your IPv6 address, and it will convert it back for you into a reverse entry. Easy way of doing it if you want to do it that way. So it really comes down to where you want to control your DNS in the end.
Okay, that's probably about all we've got time for right now. I imagine some of you have now set yourself some homework. But Brent, I want to thank you very much for your talk. That's a little gift from us here at the conference. Are you going to be around for conversations later?
Come and tackle me. And I'll say again, Terry, take advantage of Terry. If you are around on Friday and you do have time to attend his session on Friday, you will learn a hell of a lot from him. If you do want to further your knowledge into IPv6, take advantage of it while we've got him here. Thank you.
Lovely, thank you.